Okay, hello everyone. My name is Davide. I'm from the Polytechnic University of Turin, and today I'm going to present a talk on behalf of the main author of this research, who unfortunately couldn't make it here today. And this talk is about analyzing the performance of WireGuard, and specifically in multi-tunnel setups. So the agenda for this talk is the following. First, I'm going to briefly introduce WireGuard itself and also what is the problem that we found with the way it scales over multiple tunnels. Then I will have to briefly discuss what is the current design and implementation of the WireGuard module in Linux, which will allow me to make a diagnosis and explain why this problem that we will talk about in a minute happens. And finally, I will present a couple of different solutions in order to bypass or actually solve the problem. So I'm sure we all know, but just to be safe, WireGuard is a very, very common and widespread peer tunneling technology, basically a VPN, which is so widespread probably because of how simple it is, not only in its internal design, but also most importantly in how it is configured, which is, I believe, the major factor that has brought many users to adopting it. And it also generally compares very favorably with alternatives such as OpenVPN and IPsec in terms of performance out of the box. For the remainder of this talk, I'm going to assume a network topology that is similar to the one that is depicted. So basically a site-to-site configuration where we have two servers that act as the traffic generator and sink using the IPv3 traffic generator, and another couple of physical servers that will perform just WireGuard encryption and encapsulation, and on the other side, decryption and decapsulation. So these are just your WireGuard gateways. All of the servers have 32-core Intel Xeon CPUs, and all of the network links are point-to-point 100 gig Ethernet links. So let's just get started with the baseline performance file of WireGuard. And so in this experiment, we used an increasing amount of TCP flows that were being tunneled over one single WireGuard tunnel. As you can see, the performance in terms of total throughput doesn't really seem to depend at all on the number of flows that have been routed within this single tunnel, which is probably expected. And it's sitting in this particular configuration at about 5 gigabit per second. At the same time, you can see that the overall CPU utilization at both of the WireGuard gateways is quite low at less than 20%. Again, this is probably expected because I would argue that due to the fact that we're using a single WireGuard tunnel, at some point we should assume that the single UDP flow will have to be processed in a single threaded context, which is realistically producing the bottleneck. And this is actually what's happening. So a reasonable assumption in order to scale out performance is, in our opinion, to increase the number of WireGuard tunnels. And this is exactly what we did in this particular experiment. So as you can see, we used the number of tunnels up to 16 and an equal amount of TCP flows. So there was a one-to-one mapping between TCP flows and WireGuard tunnels. However, as you can see, performance only really scales somewhat linearly for the first 2 or 3 tunnels / flows, and it bottoms out at 12 to 13 gigabit per second. And what's more surprising, in my opinion, is the fact that the overall CPU utilization at both of the WireGuard gateways, or both of the sending side and the receive side, is barely increased, and it's now at around 20%. So this is undoubtedly a problem because all of these tunnels are independent to each other. So there's no apparent reason why they couldn't just automatically spread over all of the available CPUs and achieve a 100% CPU utilization. We zoom in onto the CPU utilization on a per core basis for the receiving gateway. We see that the problem is that this utilization is in fact not evenly spread across all of the available cores. In fact, as you can see, we have one core which is just pinned at 100%, is realistically bottlenecking the entire pipeline. In order to better understand what is going on here, I will have to explain some details of the WireGuard design. So as you know, WireGuard is implemented in Linux as a kernel module. And I want to explain this design by zooming in into both of the two gateways. So let's start with the sending side. Also, I am disregarding the return traffic for TCP. So let's just assume that the gateway on the left performs transmission and the gateway on the right performs reception and decryption. So the entire packet processing pipeline for the transmission gateway is composed of three separate stages. The first one is, unsurprisingly, the usual NetDev software queue that Linux uses to first receive the packets. And in this picture, I'm also assuming a technology such as RSS, receive side scaling, to spread the incoming packets over the multiple available CPUs. And also this depicts the ideal case where there's an equal amount of incoming flows to available CPU cores, and RSS is able to perfectly map those in a one-to-one configuration, which is not guaranteed. So in this first stage, we perform everything up to routing, where the packets are routed to the output WireGuard interface. And WireGuard at this point will perform some routing logic of its own to determine the destination peer. Then a couple of things happen. So first of all of the packets are enqueued onto a peer queue, which is a FIFO queue, in order to basically retain the information of the ordering of the packets. So this is later used to make sure that the packets are output in the same order in which they were received. Then the packets are moved over to the encryption stage. WireGuard uses a work queue, which is CPU-wide, to perform encryption, which means that even if we were just dealing with a single flow, the encryption load would be spread across all of the CPUs, and it would be parallelized. Finally, the last stage is transmission. To host the transmission function, WireGuard will spawn a dedicated per tunnel kernel thread, which just dequeues packets from the peer queue and sends them out by writing to a UDP socket. I guess it's very, very straightforward. Moving over to the receive side, again, assuming a single WireGuard tunnel, the first couple of stages are identical, really. So we first have the NetDev software queue that receives the packets. The only notable difference in this case is that the packets are going to be encrypted and encapsulated into a single WireGuard tunnel. So RSS is not going to be particularly useful because they are all going to look like belonging to the same UDP flow, of course. At this point, the packets are delivered up to the WireGuard UDP socket, which will again identify the sending peer and retrieve all of the information necessary to later decrypt these packets. Once again, we move over to the decryption phase, which is basically identical to the encryption one. So we first have a peer queue, which we're going to write packets into in order to remember of their order. And then the actual decryption is performed within a parallel work queue. The real difference is in the last stage. So the last stage of packet reception is what we call forwarding, which basically means taking the decrypted and decapsulated packets and delivering them to the upper layers of the stack. In this particular site-to-site deployment, it then means transmitting them over to an output interface. Now, interestingly enough, this function happens on a second instance of the network software queue. And this is because in WireGuard, each tunnel is associated with a NAPI device, the polling function of which is used to run this forwarding function. But a very interesting detail, which is also necessary in order to understand the next section of the talk, is how WireGuard decides on which core to spawn this software queue. The process works as follows. Basically, after a packet has been decrypted on a decryption worker, the worker will query the NAPI device associated to that tunnel to check whether it is currently being polled in a software queue. If it is, then nothing needs to be done because that packet will eventually be dequeued by that software queue and forwarded. Otherwise, the decryption worker will need to schedule a software queue on that same core. So as you can see, there isn't a fixed setting for the core that will host this function on a per tunnel basis, which is the source of the problem, as we'll see. So now that we've got this out of the way, we can actually try and understand what is going on in this graph. So let's try to annotate it. First, we see that, remember that this graph is referring to the receiving side of the gateway. So we have a baseline of, I'd say, 15 to 20% across all of the available CPU cores, which is where packet decryption happens. If you recall, packet decryption is parallelized as it happens on a work queue. Then on this 8-tunnel experiment, we see 8 CPU cores that have a utilization which is in the range of 35 to 40%, which is where the first of the 2 software queues is hosted. So we have 8 different cores that do this because, again, RSS is able to differentiate between the 8 UDP flows. And finally, this leaves only the last of the 3 stages for the problematic core. So in this core 30, we have all 8 of the forwarding NAPI poll functions all clumped together on the same core, which is a problem. And we call this phenomenon the NAPI black hole condition. And it would happen basically every time as long as there was enough traffic on all of the flows. And the reason why this happens is as follows. So the initial condition is such that all of the CPU cores are equally as likely to be selected to run this second software queue, the forwarding software queue. This is because if you remember from a minute ago, this core is selected as the last core on which a packet decryption happened. However, in a multi-tunnel setup, due to random chance, at some point, and usually quite soon, 2 or more of these functions will end up being scheduled on the same software queue. Whenever this happens, the natural result is that all of the NAPI devices that share the same software queue are going to be slowed down, meaning that they will take a longer amount of time to process an equal amount of packets, which in turn determines that from the point of view of the packet decryption workers, they will have a higher chance of seeing the NAPI device already being polled rather than having to schedule a new one. So the process of scheduling a new software queue to poll these devices becomes decreasingly frequent, and eventually all of these devices, all of these poles tend to clump together on the same core and become monolithic, basically never being migrated again as long as there's traffic. So what is the solution? Again, we have found a couple of different possible solutions for this problem. First one is what I refer to as a more lazy solution, because it only really involves changing some configuration parameters. And so in this particular case, this is enabling the threaded NAPI operating mode on all of the WireGuard virtual devices involved in these kind of experiments. So NAPI allows this alternative operating mode, which is called threaded NAPI, which you can just freely enable on any device just by writing to the associated CSFS node. And whenever you enable threaded NAPI for a device, what happens is that the polling context is moved from the high priority network software queue to a dedicated kernel thread. It is preemptible. So you can probably see how this solves the problem, because all of these kernel threads will now be subjected to the Linux scheduler, migrating them and making sure that they will not just end up on the same core, but rather their load will be spread out on all of the available CPU resources. So does this work? Yes. As you can see, this gains us about 4 times the throughput. We are now able to reach almost 50 gigabit per second on the same hardware, in the same configuration. And also, crucially, we can now finally saturate the CPU. As you can see, the CPU utilization in this case is 100% after 16 tunnels. But we can do better. And this is what we call the WireGuard inline. And this is an alternative design to the WireGuard module itself. So the name probably gives it away. But what it does is just, it basically moves the entire packet processing functions to be performed in line within the same context that first received the packets. So in our site-to-site configuration, this means the network software queue that receives the packets, but it could also be a system call if you're dealing with locally generated traffic. So the reason why these can improve performance is because it basically gets rid of a lot of cache locality issues, and also it just gets rid of a lot of synchronization primitives that are just straight up not necessary anymore. For example, before we had a parallel work queue that would perform both encryption and decryption, which means that the workers would need to wait for packets to be available, and then the packets would need to be potentially moved over across CPUs, which is potentially not very efficient. So once again, this gives us an extra 2x performance multiplier on throughput, and we can now basically saturate our 100 gig links. We reach just above 90 gigs over 32 tunnels. And or equivalently, you can see how the CPU load is halved at equal speed. Of course, the one downside of this technique is that it will decrease throughput in the single tunnel configuration. And this is, of course, because you're not using parallelization when dealing with packet encryption and decryption. Although in our cases, the hit was about 20%, which is significant. But if you're going for maximum throughput over multiple tunnels, this is probably an afterthought. So yeah, to conclude the talk, we saw what is one of, in our opinion, the biggest problems of the current implementation of WireGuard in the Linux kernel. And we proposed a couple of different solutions to first bypass the issue and then to properly fix it with an alternative design. So yeah, this concludes my talk. I'm happy to take any questions, if there are any.
So 2 questions. One is like threaded NAPI pretty new, but is there any real downside to enabling it? I mean, it's new and it's not been enabled by default, but feels like in this case, just like, enable it not from the knob, but from sysfs or whatever, but just from the code itself. There's some drivers doing that now for their NAPI, which really I believe the reason it was added was that some drivers really wanted it that way because it works much better. So, is there any downside to it? Like that's a 1-line patch basically, right?
Yeah, none that I'm aware of, really. There might be, but.
Okay. And then the second question would be on the inline design. Does that have any implications on the security design because you're getting away from that queue model? And I don't know. I do Wi-Fi, so we have issues with the security model. I don't know WireGuard that well, but that have implications on how you handle like maybe packet sequence numbers or something like that?
Not really. I mean, we haven't done any extensive analysis on that front. However, really kind of a minor redesign in that we take what WireGuard was already doing and we change where everything is called from, basically.
So, right. I'm just thinking that there was probably a reason they did a queue per peer, right? And so that, I'm not sure you really have that queue anymore. So that
okay, so that queue still exists in the receiving side of things. But the reason why it was introduced in the original code is, I assume, because it needed some way to make sure that the packets were transmitted out of the system in the same order in which they were received.
Right, but the idea of RSS is that you don't really care about the order between flows.
Yes,
right?
But when you move the packets to the decryption or encryption work queues, then you can get packets that are encrypted or decrypted out of order, even in the single flow, because you would break the flow over multiple cores.
Okay.
So it was really impressive throughput. Is it special at all? The traffic, is it like large packets?
No, these are just
IMIX,
elephant TCP flows.
Elephant. Okay, so big packets.
I mean, yes. Although we use standard 1500 bytes.
Yeah. Okay, cool. And did you? I was confused by it earlier slide. Can you go back to the one where you said it? That one. Yeah. So when you say it, you keep it on the same. Oh, I see. Never mind. I'm not confused. I thought they were coming in on 2 and going to 1 from the picture because it shows white, green. Yeah, actually, it is confusing. So you have it coming on multiple cores on the left, but I thought the point was that it leaves on the same core that it came in on. Is that right?
What side are we watching?
I'm looking at the left side.
Okay.
Yeah.
Yeah, no, this basically just means that there are 4 flows.
Yeah, and they come in on 4 CPUs, yes. But
I'm not sure what the confusion is about here, but basically what is happening on the transmission side is we're receiving packets over multiple cores, and we're not sending these packets over different cores to perform encryption, basically. So we're keeping the packets on the same core that they were received to encrypt them and also to transmit them out of. That's all it is, really. But yeah, potentially we are doing transmission for the same tunnel from different cores, but this is fine because different cores will be handling different flows. So if the packets get, interleaved, not a problem. And also transmission is just writing to a UDP socket, so it's thread safe.
Your picture shows it only going on one core, but you're saying it goes on any number of cores, right? That's my confusion.
Only goes on one core. Sorry, what? There's one UDP socket per tunnel or per tunnel. If you have one tunnel, there's one UDP socket. If you have n tunnels, there's n.
So my question is, are you only using one core for the routing, decrypt, and forwarding?
Yes, but this is for the reception of one tunnel. So here we are able to achieve 90 gigabit per second over 32 tunnels, and we have 32 CPU cores. So there's a
so it's going out many. It's not going out just one.
Yeah. All of these.
That's what was confusing me about the picture. It shows only going out one.
No, I can see that.
Okay.
All of these pictures are referring to just one tunnel.
Yeah. Okay.
Can you go back to the slide for the end line, the performance? Yeah, that slide. So between 1, 2, 3, 4, and around 6, is that scaling linearly?
Yeah, pretty much.
How do packets wind up on those different CPUs, right? So say you have 2 tunnels doing RSS. At it's likely at some point both of those will wind up on the same CPU, right? What's the trick here?
This is an excellent detail that you just spotted. We basically configured the queues of our NICs manually for these experiments in order to send flows to CPU cores manually. Yeah. So
this requires special hardware, or is it just a natural consequence?
So the NICs that we used allowed us to configure the queues this way. But I mean, this is just for getting the nice linear scaling. This will help even if you don't do this and just rely on RSS. It's just that it's probably not gonna scale this nicely, probably.
Okay, thank you.
All right, so people can hear this question. The redesign, the inline, those, the limitation that now you basically have parallelism with flows. It's a pretty big limitation. The original, when Jason Donenfeld presented this at LPC, he had this beautiful picture of sort of a ring between the CPUs, and they do work sharing. So I think this goes quite directly, against his idea. It's not by chance that he knows that. I'm curious on the actual lock contention. If you looked into what is the lock or cache contention, and can we do like relatively surgical changes there to scale better linear? Because 32 cores is not even that many.
Yeah, no, I agree completely. There might be a less intrusive way to achieve similar results, and also to not penalize the single tunnel performance this much. However, this is, in our opinion, this is just a first look at a way to kind of bypass this limitation that we found.
Okay, thanks. Yeah, that's interesting. I would find it very interesting to understand what the contention is and whether we can actually that without having to change the behavior, because I'm afraid that what this can lead to is that people who have big flows are using multipathing and doing very complicated things to work around what's essentially a limitation of the software.
Yes, I can totally see that.
Yeah, so one question I had, if you go back to I think it's the first slide in terms of the input, although it's more or less the same as what you had actually. Yeah, so sorry. So if you can go back to the slide that had the multiple inputs being combined into one outgoing flow. Yeah, more or less here. So one question I would have in terms of your initial problem case, were you seeing any drops at the individual queues, or were you seeing the back pressure from the device push out into drops on the NIC in just general?
This is an excellent question, which I cannot answer. I don't know.
Okay, because one thing I've seen in the past with some NICs is in this graphic here, say CPU 0 is running slow,
and say the traffic's coming in a vertical order instead, if that first CPU gets bound up, it basically backlogs all the others. And then what you see is this nice clean graph where all the CPUs are using the same amount, but it's not 100% because the one CPU is causing all the traffic for the other flows to drop. That might be one thing you want to look at is in terms of your NIC configuration, figuring out if your drops are for the entire device or per queue when a single flow gets backed up. That might actually cause some additional issues with what you've seen. So,
okay, thank you for the suggestion.
Can you go to the slide with the inline where you're showing this? Yeah, this one. So, do these span out after they are decrypted to multiple NAPI threaded instances, or it just goes to one NAPI ID and just goes to one?
So in the WireGuard inline design, we are not using threaded NAPI, but for the receive side, there is still technically a second NAPI polling instance, which most likely will be run on the same software queue of the one that actually first received the packet. So if we look at this side of the slide, there's going to be, on most cases, a single network software queue that runs two polling functions.
Just for clarification, we're still discussing, is this one tunnel in between these two, or are there four?
There's just one tunnel.
Right.
One tunnel with 4 flows routed within it.
I mean, we have a solution IPsec for that. We use multiple tunnels, and we pin each tunnel to one CPU, and then we have distinct SPIs, and then you can distribute on the receive side too. Look at RFC 9611, so we define that.
Right, thank you. There are no additional questions. I guess this concludes my session. Thank you.